My name is Christina Quintero, and this is my lab on the motion of a falling object. The point of this lab was to observe a ball of colored paper falling and attempt to predict its motion using Newton's second law. Tracker was used to extract data from the video taken, then using VPython, two computer models of the motion, one model with the weight force as the only force working on the object, and one with both gravity and air resistance working on the object were created. The data obtained from these models was then compared with the data gathered from Tracker, thus showing when drag force is not taken into account, Newton's second law overpredicts the distance traveled by the object, and that the model incorporating air resistance is more accurate. The main principle used in this lab is Newton's second law, which states that acceleration is produced when a force acts on a mass. This can be written as V final equals V initial plus F net over m delta t. In lab 1, we saw when F net equals 0, V final equals V initial. Now that F net no longer equals 0, the velocity will change over time until it reaches a terminal velocity. For this lab, F net initially equals the weight force plus the drag force until terminal velocity is reached, where the drag force equals the weight force, making the net force equals 0. This is because gravity is pulling down on the object while the air exerts an increasing force in the opposite direction until they are equal to each other. This is a video of the motion. The system is the crumpled red piece of paper. The origin is located at the paper's starting point, and the paper moves in the negative y direction. The position graph is curved, which means there is acceleration, while it seems to straighten at the end. The initial position, negative 0.026 meters, and final time, 0.602 seconds, are used in the VPython codes. Both computer models contain the same initial conditions, and both use Newton's second law and the position update equation to input the physics on the model. In the first model, where only gravity is used, F net is equal to the weight force defined by these lines of code. When we run the code, it looks like this. At first glance, it looks correct, but we will investigate that in a minute. For the second code, drag force is taken into account. For this code, F net equals drag force plus weight force. Drag force equals negative b times the magnitude of velocity squared times the unit vector of velocity. This can be written in code like so. B is the proportionality constant, which was found using the final position given by Tracker and trial by error. When we run our code, it looks like this. Using all the data collected from Tracker and the two computer models, a graph can be made and used for comparison. When the drag force is not taken into account, the model overestimates the distance traveled by the paper. This is because if there is no force acting in the opposite direction, the object will continue to accelerate, causing it to go farther. The model that took drag force into account is more accurate. This is because there is now a force, drag force, acting in the opposite direction of the weight force, causing the object to eventually reach a terminal velocity and stop accelerating, because F net equals 0, indicating a constant velocity, as proven by Newton's second law. Now to answer the lab questions. For the what does it mean question, the model using drag force predicts a terminal velocity. Being that the paper didn't reach terminal velocity in the 0.602 seconds it ran, I ran both codes for 3 seconds. Comparing the velocity versus time graphs for both models, the model using drag force has a horizontal slope at the end of the graph, showing a constant velocity, which is also the terminal velocity. The other graph has a negative slope, indicating a constant acceleration in the negative y direction, meaning there is no terminal velocity. For the what if question, if the object was thrown down rather than dropped, the drag force would actually be greater than the force of gravity. This would initially cause the object to decelerate, but would then come to the same terminal velocity, because terminal velocity is solely dependent on mass, surface area, and density of the medium the object is falling through. This can be seen when I set the initial velocity of the code using the drag force to 10 meters per second. The deceleration is indicated by the concave section and the terminal velocity by where it levels off. Thank you for watching!